Hi everyone, welcome back to another video. So this is part 3. I know that says part 5 or 6, whatever that is. But yeah, this part 3, if you haven't already, go back and watch part 2 and part 1. We're basically going through this Mechatronics book. I'll show you the title quickly. This book here. We're going from Mechatronics, Electronic Control Systems in Mechanical and Electrical Engineering, 6th edition by William Bolton. So I'm getting ready to study my Instrumentation and Control module, and as part of my preparation for that, I'm basically skimming through the books that my lecturer has recommended. He's put on our list of essential readings. So I'm skimming through the whole entire book, and in the last 2 videos we spent the last 2 hours skimming through and taking notes. I'm converting what's the information that's in the book into notes on my Notion note-taking app. As you can see, all of the notes here. So we're going to crack on, and hopefully in this video we'll finish off this book. And as you can see, I've taken a fair amount of notes. So we're moving on to microprocessors, right? And we are on part 4. I'm not very good at Roman numerals. Yeah, so part 4, microprocessor systems. So let's get into it. So chapter 10. If we take a simple control, so we're on the control part now. What's interesting is that I've actually got notes. Okay, it's fine, doesn't matter. Okay, so I was initially hoping that this was going to be notes just for instrumentation, but this is instrumentation. I also put control, and then I also put the programmable logic things. What I can't remember what they're called. Programmable logic something. PLM is called. What's it called? Programmable logic controllers, PLCs. Yeah. Okay, so we're on to control. Alright, so if we take a simple control problem, okay, the sequences of the red, amber, and green lights. I actually mentioned this in video 1 about traffic lights. Then it should be possible to solve it. I'm really interested in traffic lights and traffic crossings. I don't know why. Every time when I'm driving around, Leeds or Bradford, I'm looking at the lights and I'm thinking, okay, this changes, and I'm looking at how they vary depending on whether someone presses the crossing button or not. I find it very fascinating. Okay, so then it should be possible to solve it by an electronic control system involving combination of sequential logic integrated circuits. However, with a more complex situation, there might be many more variables to control in a more complex control sequence. The simplest solution now becomes not one of constructing a system based on hardwired connections or combination of sequential logic integrated circuits, but of using a microprocessor and using software to make the interconnections. Okay, the microprocessor system that we are concerned with in this book are for use as control systems and are termed embedded microprocessors. Okay. In this module, the microprocessors used are termed embedded microprocessors. Okay, I'm right with that. This is because such a microprocessor is dedicated to controlling a specific function and is self-starting, requiring no human intervention, and completely self-contained with its own operating program. Cool. So this is like the definition of embedded microprocessor. Microprocessors are this. Let's do it like this, and then cool. I'm right with that. Okay. All right. So let's go on to microprocessor systems. So as I mentioned, we're skimming through, right? So if you haven't watched the last 2 videos, I'm not reading the whole paragraph. So systems using microprocessors basically have 3 parts: a central processing unit, CPU, input and output interfaces, and memory. Okay, so 3 parts of systems: CPU, input, if I can do it from memory, input outputs, Oh, I can't type, man. Input output. I need to get a different keyboard. Sorry about that. Input output and memory. Input output interfaces. Okay. Okay. Oh, we're lagging a bit. All right. So buses, I kind of already know what buses are. And maybe we can just put a basic definition of buses. Digital signals move from one section to another along paths called buses. Okay, so let's do this. Types of buses. And then we'll put data bus, address bus, and control bus. Data, address, what was the other one? Control. Okay. Can we turn this into a bulleted list? Yep. And we've got the microprocessor. The microprocessor is referred to as the central CPU. Okay. And just what it's made up of. So I know this already because I studied this in the first year. So I probably don't really need to go into it, but let's do bulleted list. And then we've got ALU, registers, control unit, accumulator register. The number of types of registers, the number, size, and types of registers varying from. Okay, so this is different types of registers. Okay. Types of registers. I can't really see us going through this. Accumulator register, status register, or condition code register, flag register. And program counter register, or instruction pointer. Memory address register. So we covered all of this in what was the module? Computer systems architecture. General purpose registers and stack pointer registers. So what are they? Accumulator register, status register, program counter register, memory address register, instruction register, general purpose registers, and stack pointer register. I actually have a decent idea of what each one of these are actually. Okay, so let's go into memory. The memory unit in the microprocessor system stores binary data and takes the form of one or more integrated circuits. Today may be program instruction codes or numbers being operated on. Oops. Okay. There are a number of types of forms of memory unit: ROM, PROM, EPROM. ROM, PROM, EPROM. Alright, so we're writing down basically different types of memory or different forms of memory unit. Okay, so we got ROM. Let's do a bulleted list. ROM, PROM, EPR, ROM, EP. Was it ROM, PROM, EPROM? Yeah, EEP, ROM, EEPROM as well, and then there's RAM. Okay. Then we're on to, so this is memory, and then we've got input outputs. Okay, the input output operation is defined as the transfer of data between the microprocessor and the external world. Transfer of data between the microprocessor and the external world. The term peripheral devices is used for pieces of equipment that exchange data with a microprocessor system. Okay, like a mouse and keyboard, and a microphone, camera, etc. Taking the external world and putting it into the computer, and vice versa. Like speakers, taking the microcontroller and putting it into the external world. I'm right with that. Okay. Examples of systems. We're going to skip that. Skip that. Microcontrollers. For a microprocessor to give a system which can be used for control, additional chips are necessary. For microprocessors to give a system which can be used for control. What? That must be an error, because that doesn't even make sense. For microprocessors to give a system which can be used for control, additional chips are necessary. E.g., memory devices for programming data, storage and input-output ports to allow it to communicate with the external world and receive signals from it. Okay, something's missing there. Let's just, what are they trying to say? For microprocessor, additional chips are necessary for it to get control. The microcontroller is the integration of a microprocessor with memory and input-output interfaces and other peripherals such as timers on a single chip. Okay. So this is the part that we're after, really. I don't understand what they're trying to say in the first part. So microcontrollers, and just what it is. Yep. That's a picture of a microcontroller. Oh, sorry, not a picture of a microcontroller, block diagram. Okay, comfortable with that. Motor free scale, yep. Yep. I'm alright with that, I mean, I'm not alright with this, but I'm just going into a lot of detail here, which I'm not trying to get caught up in the weeds. Microchip microcontrollers, another widely used family. Okay, that's fine. Just families and stuff, examples. So all of the examples I'm just skipping over. Don't need them. All of the intricate details, again, I'm skipping over. Why? Because the point of this is just it's like a subject overview, right? I'm not learning the subject yet. Okay, what's this? Oh no, okay. Arduinos and stuff like that. Selecting a microcontroller, number of inputs, interface required. Okay, yeah, that's fine. Applications, temperature measurement system, domestic washing machine, programming, define and program, pseudocode. Yep, I'm right with all of this. Problems. Okay, so language. So now we're on to programming, assembly language, and then we're gonna go to C, right? Yep. Addressing. Yep. We're comfortable with all of this. It's quite cool actually how they explain how they've gotten to programming. You think about like from sensors and stuff to gears to microprocessors. They've built up quickly. Okay, so all of this is assembly programming. If you haven't done it before, you're gonna look at this and say, "What is all of this jargon?" But assembly programming is not too hard actually. Subroutines, I'm comfortable with all of that. Yep. I'm comfortable with functions, loops, nested loops. I'm alright with that. Delay with a stepping motor. Okay, just giving you an example using assembly programming. Embedded programming. In an embedded system, the manufacturer makes a ROM containing the program. This is only economical if there is a need for a large number of these chips. Alternatively, for prototyping or low volume applications, a program could be loaded into the EP ROM of the application hardware. The following illustrates how the EEPROM of microcontrollers can be programmed. Okay. It's about programming the chips. Again, I'm not too bothered by this. I assume this is what I'm going to be doing a lot of in embedded systems. So again, C programming language. If you're planning on being an electrical engineer, then C programming is definitely one thing you want to get strong at. Me personally, this year I'm going to take a bit of a break with the C programming, just because I feel like I'm already enjoying it and I can pick it up at any point. If I pick up C programming for a month and just get through some books, I'll be alright. Pointers. It's funny whenever I speak to anyone about electrical engineering, programming, computing, anything like that, and I mention, oh yeah, I did C. The first thing they ask is, how are you with pointers? Do you know pointers? What's pointers? It's like you can't, if you're okay with C, then you better be okay with pointers. And then the next thing that they always ask is, well, what about memory management? And they're like, do you know what's malloc? So yeah, it's interesting. Yeah, if you can understand pointers and memory management, as in I don't understand memory management, but malloc and stuff like that, then you'll be okay. Okay, so now we're on to chapter 13, input and output systems. So we'll carry on taking notes for this. I mostly just skip through the whole, pretty much, the whole part of that programming chapter. Alright, so interfacing. When a microprocessor is used to control some system, it has to accept input information, respond to it, and produce output signals to implement the required control action. It has to accept input information, yep, respond to it, and produce output signals to implement the required control action. Okay, yep. So you press like K, and then it understands you press K, and then prints that onto the screen, right? So you think about, like, you press K on the keyboard, goes to the microprocessor in your laptop, and then that laptop sends an output signal through your display cable to your display, right? Thus, there can be inputs from sensors to feed data in and outputs to such external devices as relays and motors. Okay. The term peripheral is used for a device such as a sensor, keyboard, actuator, etc., which is connected to a microprocessor. However, it is, not normally possible to connect directly such peripheral devices to a microprocessor bus system due to lack of compatibility in signal form and levels. Because of such incompatibility, a circuit known as an interface is used between the peripheral items and the microprocessor. Okay, yeah. The interface is where the incompatibility is resolved. Okay, so I kind of want all of that information there because that's quite good information. Interfacing, this and that. Okay. It's frustrating how Notion copy and paste in. Very frustrating. Anyways. Okay, so when the microprocessor is used to control some system, it has to accept input information, respond to it, and produce the microprocessor. Right. Accepts input information, responds and produces output signals to implement the required control action. Okay, yep. Thus, there can be inputs from sensors to feed data in and outputs to such external devices as an output to external devices. So I'm just trying to make it so it's more easily readable for me when I'm revising and going back through and creating flashcards and stuff like that. The term peripheral is used for a device such as sensor, which is connected to the microprocessor. So it's not connected. Let's put peripherals. Peripherals are not connected directly to a microprocessor bus system due to lack of compatibility. A circuit known as an interface is used. A circuit known as an interface is used between the peripheral items and the microprocessor. Right, cool. And then let's just get that picture of that block diagram that they had as well. There we go. So we've got the peripheral, the interface, the microprocessor, interface, peripheral. Okay, I'm alright with that. So input output addressing. There are two ways that microprocessors can select input output devices. Some microprocessors have isolated input output and special input instructions. Okay, well, what? There are two ways that microprocessors can select input output devices. Some have isolated input output, and I assume, where's the second type? More commonly, microprocessors do not have separate instructions for input output, but use the same instructions as they use for reading from writing to memory. This is termed memory mapped input output. Okay, so that's all a bit complicated, but let's just put two types of, what are we talking about again? Two types of two ways of selecting input output. Two ways of selecting input output, right? So you've got the isolate input output and special input instructions. That's one, right? And then number two is memory mapped input output. And I'm not bothered about what these mean. I don't know what those mean. Like I said, just trying to get a nice overview of what we're talking about and not really get into the weeds. So input output registers. The Microcontroller microcontroller has 5 ports. Blah blah blah. Okay. Again, I'm not interested in specifics of certain devices or whatever. Interface requirements. The following are some of the actions, especially because a lot of this stuff that's being taught, if this book was written in 2012 or whenever it was written, would be out of date now anyway. So I'm only interested in currently right now the broad overview, the macro. Okay, so interface requirements. The following are some of the actions that are often required of an interface circuit. Some of the actions that are required. Okay, so got it. Actions of interface circuit. Electrical buffering isolation. What? Okay, there you go. Timing control. Again, I don't know what these words mean. Code conversion. Changing the number of lines. But like I said, I'm going to study all of this individually in detail, step by step. You know, building upon each part that I study. Usually when I'm going through a book like this, and let's say I was going through this part, conversion from analog to digital and vice versa. Just this one chapter probably take me 15 minutes, and I'll watch a YouTube video on it, and you know, I might I'll read this paragraph, and then I'll Google it and try to read other definitions. That's how I like to come to my understanding on topics. Which in future videos I'll start going through, and you'll see me as I go through learning these different topics. So a buffer is a device that is connected between two parts of a system to prevent unwanted interference between the two parts. Okay, that's fine. So let's just put buffer, and we'll just copy and paste that definition in there. An important use of a buffer is in the microprocessor input port to isolate input data from the microprocessor data bus until the microprocessor requests it. Interesting. That makes sense. Yeah, comfortable with that. So buffers, a logic change enabled by 1. Okay. Alright, handshaking. Unless two devices can send and receive data on identical rates, handshaking is necessary to exchange data. With handshaking, the slower device controls the rate at which the data is transferred. Okay, that's cool. I'll just put that there and leave it at that, because then you can see it gets a bit more complicated. Handshaking. So another way of putting this is that I just want the 5-year-old definition. Give me the 5-year-old definition. Which would be pretty cool. Imagine if you went to university and they just said, look, we're going to teach you every single topic in electrical engineering, but we're going to give you the 5-year-old version of it. I'd know more now than I did. I definitely know more now than I do. All right. So, polling and interrupts. Consider a situation where all input-output transfers of data are controlled by the program. Consider the situation where all input-output transfers of data are controlled by the program. Okay, when peripherals need attention, they signal the microprocessor by changing the voltage level of an input line. The microprocessor can then respond by jumping to a program service routine for the device. On completion of the routine, a return to the main program occurs. Yeah, I don't know. Okay, I got it. So, program control of inputs and outputs is thus a loop to read inputs and outputs update outputs continuously, with jumps to service routines as required. This process of repeatedly checking each peripheral device to see if it is ready to send or accept a new byte of data is called polling. Okay, so it's the fact that the program keeps jumping to the peripherals to check them, and that's called polling. Okay, got it. Polling. Let's put it in here. Okay, so program control of inputs and outputs is thus a loop to read inputs and update outputs continuously. Don't need this bit. This process of repeatedly checking each peripheral device to see if it is ready to send or accept a new byte of data is called polling. Got it. Okay. Interrupts is actually interesting. Okay, because it's polling and interrupts. All right. So an alternative program control is interrupt control. An interrupt involves a peripheral device activating a separate interrupt request line. The reception of an interrupt results in the microprocessor suspending execution of its main program and jumping to the service routine for the peripheral. Got it. So polling, and then we got interrupts. If anyone knows how to copy and paste into Notion without formatting, should we Google it? Let's just put how to copy and paste in Notion without formatting. Pasting in paid text, that was it. Create a code block, space it in there. That's what I do when I'm doing rapid note taking. Good tip. I just tried this. That works as a placeholder for now, but ideally, I'd be able to just match the how you actually know this is Control Shift V. Okay, so you can do it in the browser, but not in the app. Okay, so I might just use the browser from now on. Paste text fast and text such as Sublime. Yeah. So basically, you can't do it, but you could do it in the browser. That's interesting. So I might just use the browser. Studies, second year, Instrumentation Control, and Notes on Mechanics. See how nice Notion is? It's beautiful. And literally, look, it will update in here everything quickly as well. Interrupts. Okay, cool. So I think I was using the Notion app, so I'll use the browser for now. Okay, so let's just see. Can I copy and paste in without Control Shift V? Oh, it doesn't even do it. Paste is plain text. It doesn't do it. Well, I could do it up here first and then down here. Okay, whatever. It's fine. Doesn't matter. Okay, so this is all about the interrupts. We don't want to go into the weeds here. Serial interfacing. With the parallel transmission of data, one line is used for each bit. Serial systems, however, use a single line to transmit data in sequential bits. There are two basic types of serial data transfer: asynchronous and synchronous. Okay, so right, and then so with parallel transmission of data, one line is used for each one bit. Serial system, however, uses a single line to transmit data in sequential bits. Okay, so let's put parallel versus serial for one. Copy and paste that in there, and then down here. Okay, and then just put that. Yeah, serial parallel. Okay. So then we've got there are two types. So asynchronous versus synchronous. Okay, and let's define them. So asynchronous transmission, the receiver and the transmitter each use their own clock signal, so it is not possible for a receiver to know when a word starts or stops. Okay, so they're basically working separately. Let's set a title here. Okay, and then where's synchronous? Okay, so with synchronous transmission, the transmitter and receiver have a common clock signal, and thus transmission and reception can be synchronized. Got it. So I don't care too much about how my notes look, but I do care a little bit. I care enough to try and use, bolding and headers and stuff like that. Okay, so peripheral interface adapters. Okay, I'm going to skip this. I mean, what I'm choosing to skip versus not skip, it's mostly subjective, and it can be. It's your studying, so do what you like. Initializing the PIA before I don't even know what the PIA is. Okay, peripheral interface adapter. Okay, so I'm gonna skip that. Skip this whole bit on the adapter part. Serial communication interfaces. The universal asynchronous receiver and transmitter, the UART, is the essential element of a serial communication system, the function being to change serial data to parallel for input and parallel data to serial for output. A common programmable form of a UART is the Asynchronous Communications Interface Adapter, ACIA, from Motorola. Okay, I'll leave out the example bit and just put this bit in. Okay, let's go here. Serial communications interface. The universal asynchronous receiver transmitter is the essential element of a serial communication system. Okay, pause that there, and then I want less words. It changes serial data to parallel for input and parallel data to serial for output. Cool, I'm alright with that. Serial interfaces of microcontrollers. Many microcontrollers have serial interfaces built in UARTs, for example. Yep. Okay, I'll skip that. Examples of interfacing. Interfacing 7 sync display with a decoder. Consider when the output. Okay, just examples again. When it gets specific, I skip. Okay, interfacing analog. Digital to analog conversion is required when the output from a microprocessor or microcontroller is required to provide an analog signal output, of course. For example, the DAC, okay, can be used if the latches. Alright, that's kind of a given. I'm right with that. If you told me how would you get a microcontroller to interface with an analog meter, then I would say you'd have to obviously convert the output signal to analog. So we've got a summary here. Okay, I'm fine with that. Alright, so on to the next chapter, chapter 14. So we're in chapter 14 and there are, I believe, 24 total chapters. Yeah, so we're more than halfway now. And yeah, I mean, it's still a fair bit. System models, stuff like that. Yeah. Okay, let's carry on. Okay, so we're moving on to programmable logic controllers now, which is one of the things that I've been looking forward to since I started going through this book. Okay, so programmable logic controller. And copy that in. Let's get rid of that actually. The PLC is a digital electronic device that uses programmable memory to store instructions and to implement functions as logic, sequences, timing, counting, and arithmetic in order to control machines and processes, and has been specifically designed to make programming easy. Okay, that's the official definition we got there. Okay, so let's just make sure I try and understand that. A PLC is an electronic device. It uses programmable memory to store instructions and to implement functions in order to control machines. Okay, not entirely sure I get that. Okay, let's carry on. Input devices, switches, and output devices being controlled are connected to the PLC, and then the controller monitors the inputs and outputs according to the program stored, and so controls the machine or process. Okay. They were designed as a replacement for hardwired relay and timer logic control systems. PLCs have the great advantage that it is possible to modify a control system without having to rewire the connections to the input and output devices. The result is a flexible system which can be used to control systems which vary quite widely in their nature and complexity. Such systems are widely used for the implementation of logic control functions because they are easy to use and program. So I've read that paragraph and I don't get it. I don't get it. PLCs are similar to computers but have certain features which are specific to their use as controllers. Okay. So they're rugged and designed to withstand vibrations, temperature, humidity, and noise. That's actually kind of what I was thinking about when I was thinking about a PLC. I was thinking that like a big rugged machine that you can throw about and leave it in the desert for an hour and it'll be fine. My Dell XPS would get wrecked. The interfacing for inputs and outputs is inside the controller. Interfacing for inputs and outputs is inside the controller. Okay. They are easily programmed. Okay. So let's put similar to computers. And they have certain specific features that are specific to their use as controllers. Then ugh. Oh dear. Notion. I mean, although I use Notion a fair bit, not enough. Oh my gosh. I'm being extra, I think. Turn into numbered list. What's that? Turn into bulleted list. Let's get rid of the numbers. Okay. I try and make my notes neat because if they're not, you're just probably not going to go through it. The basic PLC structure shows. So figure 14.1 shows the basic internal structure of a PLC. It consists of essentially of a CPU, memory, and output interfaces. CPU controls and processes all information. So this is a PLC. Okay, I'll screenshot this, but I don't really know why I'm screenshotting this. Block diagram of PLC. One thing I'm glad about is that I now know what a PLC is. But I mean, as for how beneficial that is, I don't know. Input and output. The input and output units provide the interface between the system and the outside world. Yes, and are where the processor receives information from external devices and communicates information to external devices. Okay, we know that. The input-output interfaces provide isolation and signal conditioning functions so that sensors and actuators can often be directly connected to them without the need for other circuitry. Okay. Um. Okay, I'm going to skip all of that. Input and programs. Programs are entered into the input-output unit from small handheld programming devices, desktop consoles with a visual display unit, keyboard, and screen display, or by means of a link to a personal computer (PC), which is loaded with an appropriate software package. Only when a program has been designed on a programming device and is ready is it transferred to the memory unit of the PLC. Okay, so I suppose the key takeaway there is that you don't program the program on the PLC itself, but for what? I don't get what I'm really doing with that information, but okay. The programs are from, okay, small handheld programming devices, desktop consoles, keyboard and screen display, or by personal computer, which is a PC. Who uses the term personal computer nowadays? Which is loaded with appropriate software. Okay, so, oops, sorry. Make these bullet pointed. Yep. Okay. Forms of PLC. PLCs were first conceived in 1968. Someone gave birth to it then. They're now widely used. Okay. Input-output processing. A PLC is continuously running through its program and updating it as a result of the input signals. Each such loop is termed a cycle. There are two methods that can be used for input-output processing: continuous updating and mass input-output copying. Interesting. Okay. So let's put input output processing, right? And then termed a cycle. Okay. So two methods for processing. And then we've got continuous updating and mass input output copying. Okay, so continuous update involves the CPU scanning the input channels as they occur in the program instructions. Scanning the input channels as they occur in program instructions. Each input point is examined individually and its pertinent program determined. Okay, I get that. And then mass input output copying. Because of continuous updating, there has to be 3 millisecond delay on each input. The time taken to examine several hundred input output points can be comparatively long. To allow more rapid execution of a program, a specific area of RAM is used as a buffer store between the control logic and the input output unit. Each input output has an address in its memory. At the start of each program cycle, the CPU scans all the inputs and copies their status into the input output addresses in RAM. Okay. I'm okay with that as well. Alright, that's fine. Input output addresses. PLC has to be able to identify each particular input and output, and it does this by assigning addresses to, okay, that's fine, like at houses in the town. This is actually how I think about memory in computers, that each memory address is like a house in a town having an address, 111 Rodell Drive, something. Ladder programming, I'm going to skip ladder programming. Logic functions, again, we've already touched on this in this book, so each horizontal, okay, there's still ladders, this is all ladder programming, which I'm not going to get into. Latching and internal relays. There are often situations where it's necessary to hold a coil energized even, okay, don't worry about that. We're still in the weeds. Let's get out of the weeds. Timers. The previous section in the chapter have been concerned with tasks requiring a series and parallel connections of input contacts. However, there are tasks which can involve time delays and event counting. These requirements can be met by the timers and counters which are supplied as a feature of PLCs. Okay, timers. A common approach used by PLC manufacturers is to consider timers to behave like relays with coils which have been energized, result in the closure of or opening of contacts after some preset time. Okay, I'm going to skip this. Counters. Again, it's kind of obvious what a counter is. Shift registers. So we covered shift registers in computer systems architecture. I'll skip that. Master and jump controls, again, kind of covered that already. Jump, it's like, if statements or go-tos in programming. Data movement, data comparison. So we're back into programming, it seems. We touched a little bit on PLCs and then now we've jumped straight into programming. Okay. Summary. One thing you could do as well is you could just read the summary of each chapter, and that would probably give you, a decent overview. Maybe we'll do that on the next book. But again, I suppose it depends on how well written the summary is. Alright, so chapter 15, communication systems. Okay. So digital communications. An external bus is a set of signal lines that interconnects microprocessors, microcontrollers, computers, and programmable logic controllers, and also connects them with peripheral equipment. Thus, the computer needs to have a bus connecting it with a printer if its output is to be delivered, to be directed to the printer and printed, of course. Multiprocessor systems are quite common. For example, in the car, yep. Okay, so what point are we trying to make here? There may be need to link a PLC to a control system involving a number of PLCs and computers. Computer integrated manufacturing is an example of a large network which can involve large numbers of machines linked together. This chapter is a consideration of how such data communications between computers can take place, whether it is just simply machine to machine or a large network involving large numbers of machines linked together and the forms of standard communication interfaces. Okay, we've got centralized computer control. Involves the use of one central computer to control an entire plant. This has the problem that failure of the computer results in loss of control of the entire plant. Interesting. So they were common in 1960s, which suggests that they're not common at all now, right? Okay, yeah. All right, so let's talk about the centralized computer. Okay. So this has a problem that a failure computer entire plant. Yep. Okay, so we got a hierarchical system. With the hierarchical system, we've got a hierarchical system, we've got a distributed system. Distributed system, you know, being like a basic version of Bitcoin or something, right? So hierarchical system, distributed system. With the hierarchical system, there is a hierarchy of computers according to the tasks they carry out. The computers handling the more routine tasks are supervised by computers which have greater decision-making role. For example, the computers which are used for direct digital control of systems are subservient to the computer which performs supervisory control of the entire system. The work is divided between the computers according to the function involved. There is a specialization of computers, with some computers only receiving some information and others different information. Interesting. Hmm. I'll just copy that whole thing there because that was all fairly, it's fairly straight to the point there. With the distributed system, each computer system carries out essentially similar tasks. Okay, so each computer carries out similar tasks to all the other computer systems. In the event of a failure of one or overloading of a particular computer, work can be transferred to other computers. I've got it. The work is spread across all the computers and not allocated to specific computers according to the function involved. There's no specialization of computers. Each computer thus needs access to all the information in the system. Yep, that's cool as well. Right with that. Okay. Parallel and serial data transmission. Data communication can be via parallel or serial transmission links. Parallel data. So, wait, what? Data communication can be. Okay, we've kind of already covered this in this book as well. Go on then. Why not, right? System types. Transmission now. And we've got parallel data transmission. And we got serial data transmission. The way that I think about this, you know, I haven't, before I read these chapters, this could be wrong, but I studied it last year. The way that I think about parallel versus serial, I wonder if I could find an image of it. That would be quite cool, actually. But it's like 10 buses driving into a bus station where you have 10 exits, right? Or 10 entrances. So 10 buses all drive in at the same time, right? And then a serial data transmission would be like 10 buses lining up one by one and driving in one by one, for example, into one entrance or into a, you know, a tunnel, whatever. Yeah. I wonder if I can find a picture of that. So serial versus parallel transmission. Example. I mean, like, that's what I'm talking about in terms of buses. I actually think of like actual buses driving into let's put cars. Might be worth me actually doing this. Design a nice little graphic of some cars driving in. Serial versus parallel transmission, and then car examples, road example. No. No one's done one, man. You guys gotta do one. One of you do one, okay? Come up with an example of serial versus parallel. I'm sure some of the YouTubers must have done it, man. Yeah. Anyways, I've gone down a rabbit hole. Let's get back out the rabbit hole. Okay. The parallel data transmission. Within computers, data transmission is usually by parallel data paths. Huh? Okay, within computers, right. Parallel data buses transmit 8, 16, and 32 bits simultaneously. I don't want to get into too much. Like I said, although I've already studied this and I understand the 18, 16, and 32-bit points, I don't want my notes to be filled with specifics. I just want generalized 5-year-old examples of, like I said about the buses. That's what I want for every concept. So serial data transmission. This involves the transmission of data, which, together with control signals, is sent bit by bit in sequence along a single line. Yep. Okay. It's going to tell you about the problems, etc. Synchronous. Yeah. Okay. Serial data communication modes: simplex, half duplex, and full duplex. Okay. So let's just. I'm not going to write down what these are. I'm just going to mention that there's the 3 different types of them. So you've got simplex mode, half duplex, and full duplex. Another way that I like to look at my notes is, imagine if you was going for an interview, you didn't really know what they were going to ask you specifically, but you knew that it was going to be on a giant field of engineering, like instrumentation and control, right? So you wouldn't want to go too deep into the weeds here about what full duplex mode is, half duplex mode is. You just want to make sure that they said to you, hey, what are the serial data communication modes? Do you know some of them? You'd be like, yeah, of course, yes, the simplex mode, the half duplex mode, and the full duplex mode, right? And then if you just respond like that, they might even go on and ask you something else. But if they said to you, so what, could you explain to me what one of them are? You'd be like, to be honest with you, it's been a long time since I studied it, but you know what? Quick Google search and I'll be more than fine, even though you've never studied it. So yeah, that's the way I like to do my notes, in a way that I could be confident and have a broad idea without going, well deep into the weeds. Because let's be honest, to do this whole book, I think we're about 3 hours now into this book, right? 3 hours of skim reading. Now, granted, if I wasn't recording the video and I wasn't speaking and I didn't get sidetracked like I am being sidetracked now, probably would have done it in an hour and a half, right? Half the time. So an hour and a half to skim read a book and take notes, right? Especially if I was just skim reading without taking notes, then you're talking, 45 minutes. So if you was to read and learn the whole book, you're talking 30 hours, 50 hours. So yeah, for me, this is the perfect, it's a nice, easy, but very beneficial way to study a subject. Okay, so let's go on to networks. Okay, so the term network is used for a system which allows 2 or more computers, microprocessors, to be linked for the interchange of data. I think every human being now understands that, but maybe, maybe 10 years ago wouldn't have. Maybe 20. Okay, so what's this? So the following are commonly used forms. What are we talking about here? The logical form of the links is known as a network topology. The form of the links. Okay, so how they're formed. How they're linked together. Okay. The term node is used for a point in the network. Yep, we know that. So 1 or more communication lines terminate, or a unit is connected to the communication lines. Yep. The following are commonly used forms: data bus, star, okay, hierarchy or tree. Yeah, I actually fully understand all of those. Yeah. You got a data bus, that's a star, that's obviously hierarchy. This is going to be a ring, circle, thingamajig, and I don't know what this is. Oh, mesh. Yeah. Oh, nice. I don't know why I find that actually quite interesting. How you would set up networks. All right. Well, wherever your interest is, you should put in a bit more effort. So let's put in some effort. I would have just taken notes on just these, but I'm gonna make my notes a little bit nicer here because I'm actually quite interested in this. I'd like to specifically. I would like to dig deep into this chapter. So okay, so let's take some better notes here. Let's say the logical form of the links is known as the network topology. So how the network is formed is known as the network topology, right? Man, I can't spell. Network topology. And then you've got types of network topologies. Topologies. That. Then screenshot of that. That's cool. Okay, and then what is in here? So the term node is used for a point. So let's put node. A node is a point in the network. Where one or more communication lines terminate or a unit is connected to the communication lines. I'm gonna leave that out because that can just be confusing, especially if I'm reading that at 2 a.m. 6 hours before an exam. Don't confuse myself. Okay, so the following are commonly used forms. Okay, so all right, let's put. Okay, let's do this. Right, let's put node here. Get rid of this, and then let's talk about data bus. This has a linear bus into which all the stations are plugged. This system is often used for multi-point terminal clusters. Data bus. Okay, and then we've got star. This has dedicated channels between each station. Dedicated channels between each station. Yep, and a central switching hub is that one there, through which all communication must pass. Yep, that's fine. So if this one A or number 1 wants to communicate with number 5, 2, 3, 4, 1, 2, 3, 4, 5. Yeah, if 1 wants to communicate with number 5, it has to do so via central hub, right? Yeah. Cool. Yep. And hierarchy or tree. This consists of a series of branches converging indirectly to a point at the head of a tree. This one here. With the system, there's only one transmission path between any 2 stations. Cool. That's cool. I'm learning a lot, man. Oh, they've even done ring and mesh. Nice. Okay. So, ring. Ring mesh. This is a very popular method for local area networks, involving each station being connected to a ring. The distances between nodes are generally less than 100 meters. Data put into the ring system continues to circulate around the ring until some system removes it. The data is available to all stations. Okay. I feel like that, about one thing removing it is an important point. Ring. Let's remove. I'm not bothered about the distance thing. That. But data means circulate. Yeah. Cool. And then lastly, mesh. This method has no formal pattern to the connections between stations, and there will be multiple data paths between them. So basically, the mesh system is not like that. It's just similar to that in the sense that it's kind of all over the gaff and whatever, however the person wants to set it up. That's cool. So the type of network topologies are data bus, star, hierarchy, ring, and mesh. I don't know why. I don't get it, but I'm quite interested in that actually. The term LAN, local area network, is used for a network over a local geographic area, such as a building or group of buildings on one site. Topology is commonly bus, star, or ring. A wide area network is one that interconnects computers, terminals, and local area networks over a national or international level. This chapter is primarily concerned with local area networks. What chapter are we on now? I don't even know. Where are we on? We're on communication systems. I've got a module on communication systems, right? Yeah. Nice. So it looks like I'm probably actually going to enjoy this module. That is cool. Oh, we don't have an icon here. Let's put an icon. We'll go with that. That's fine. You pick one or the nails. Let's go with a bone. Nick nap, paddy back, give a dog a bone. All right. Okay, so let's just talk about LAN for a minute. The term local area network LAN is used for a network over a geographic area, such as a building or group of buildings one site. Yep. Topology is commonly bus, star, or ring. A wide area network is one that interconnects computers, terminals, and local area networks over a national or international level. Is that a WAN? It probably isn't it. What's a WAN, right? It is WAN, yeah. Yeah, WAN. What is a WAN? Interesting. Okay, so let's put a WAN. We go. All right, so let's finish. We've got communication systems and fault finding left of this bit, and then we've just got the part 5 system models and then conclusion. So let's finish communication systems and fault finding in this video. All right, so access control methods are necessary with a network to ensure that only one user of the network is able to transmit at any one time. The following are methods used with I thought I said right wing. With ring-based local area networks, two commonly used methods are token passing and slot passing. And then, okay, with bus or tree networks, a method that's often used is, so network access control is what this part is called, right? Yeah, network access control. Okay, so we can copy and paste that bit in, fine. And then got ring, right? And then they use token passing. Ability list, token passing, slot passing. Then with tree or what was it? Tree or bus. Ability list. And they use carrier sense multiple access with collision detection. Okay. And it's generally used with Ethernet. Generally used with Ethernet. Done. Alright. Okay with that. So broadband and baseband. The term broadband transmission is used for a network in which information is modulated onto a radio frequency carrier which passes through the transmission medium such as a coaxial cable. Typically, the topology of broadband local area networks is a bus with branches. Broadband transmission allows a number of modulated radio frequency carriers to be simultaneously transmitted and so offers a multi-channel capability. The term baseband transmission is used when digital information is passed. I'm actually I don't know, for whatever reason I'm quite interested in this. I don't know why. I don't know why I'm interested in networks. I'm quite interested when I watched the video on optical fiber optics. That fascinated me. But I want to get into renewable energy. So I don't know how much crossover is between communications and renewable energy. So I'm going to skip this for now, even though I'm interested in it. I'm going to skip taking notes of it. I'll just skip over that for now. Okay, so protocols. I assume that's an important part of communications. What's interesting is that I'm probably going to be redoing most of these notes for the communication systems module anyway. So, so transmitted data will contain two types of information. One is the data which one commuter wishes to send to another. The other is information termed protocol data and is used by the interface between a computer and a network to control the transfer of the data into the network or from the network into the computer. So it's to control the transfer. Protocol is a formal set of rules governing data format, timing, sequencing, access control, and error control. Interesting. Okay, so just go with that, right? And then we can just go with the three elements of protocol are syntax, semantics, and timing. Right, and then I'm going to get rid of the explanation. Syntax, semantics, and timing. Again, you might ask, why would you get rid of the information? But it's because I want to keep it super simple and easy to read. Okay. Open systems, interconnection, communication model. Communication protocols have exist on a number of levels. Physical layer. Okay, so the International Organization for Standardization has defined the 7-layer standard protocol system known as the Open Systems Interconnection Model. The model is a framework for developing a coordinated system of standards. Sounds like one of those important things that, you know, if you was to go for a job interview, you could possibly be asked about. What is the International Organization of Standardization? So let's just do it, even though I don't think I'll need to know this, but okay. And then so they've made a model. The model is a framework for developing coordinated systems of standards. What's interesting is you don't think about this kind of thing, but you know, if these kind of organizations and agencies didn't come up with standards, it'd be a mess. You know, you can imagine, like, back in the days, you weren't able to plug in certain things to certain things. So now things are a lot nicer for us. Okay, so number one, you've got the physical layer. Number two, you've got the data link layer. Number three, you've got the network layer. I assume these things are like, the physical layer would be like that the USB fits into the USB port. And then the data link layer would be that the data that is sent between them, they actually understand what's being sent, etc., etc. I mean, I could just read the explanations here, but I'm not going to. Okay, so there you go. There's the 7 parts of that framework. Network standards. There are a number of network standards based on the ISO OSI layer model that are commonly used. The following are examples in the United States. Blah blah blah. Okay. RS-232. I learned about this last year. Serial interface. Yeah, serial communication interfaces. Serial interfacing can involve synchronous or asynchronous protocols. Commonly used asynchronous interfaces are RS-232 and later versions, a 20 milliamp current loop IC2, I2C, CAN, and USB. Yeah, so RS-232 is like super old, I believe, right? Yeah. So defined as is RS-232 same as VGA. VGA is graphics interface, which uses RGB. The common name for RS-232 is serial for cable video. But they're not the same, but they look the same, right? It's old anyways. Yeah, not something I particularly need to know. So I'm gonna skip over. What's actually funny is, like when you work in the industry, like even as I'm saying, well, this is really old, you're not gonna have to use it or whatever. I know that Boeing, they recently just stopped using floppy disks in their planes. That's Boeing floppy disk. Oh no, they still use it as of August 2020. Yes, some Boeing 747 still run on a floppy disk, and it's like critical updates as well. Just like us in 1995, they use a sequence of 8 floppy disks to update their software. Maybe that sounds horrifying, but it's both smarter than we think to keep using these disks, and it's an interesting snapshot of the ways aeronautics continues to adapt to new technologies. I think it's one of those where it's like, hey, these fly safely using floppy disks, but we don't want to use iPads. Thank you. But yeah, so like I said, you'll find this a lot in industry. In industry, when you're working, you'll find a lot of big, huge. It's always the big, huge conglomerate companies. Small little guy sets up a 3-4 man shop. He gets everything: iPad, everything touchscreen, whatever, iMac, all of that. But in industry, they use really old stuff. So even though I'm saying we're not going to use, RS-232, as an electrical engineer and a communications engineer, you probably will actually. Yeah, so let's crack on. CAN bus. I'm going to skip over all of this for now because it's a bit in the weeds. Parallel communication interfaces. I'm going to skip over this as well, mostly because a lot of this I'm going to be covering in my communication systems module, so it's more applicable over there. Wireless protocol, and then this is a summary. Okay, and then we're on chapter 16, fault finding. So we'll wrap this video up after we finish this chapter. So what's interesting is that the way that this book has been written, I've actually kind of been able to keep up. Usually, by this time, I'm usually mad confused, when books build upon other principles. But this book seems to be bringing completely new topics to go on alongside each other rather than building on top of each other. So I suppose I've been able to learn lots from each chapter of this book as I'm going through it. So quite interesting. The fault detection techniques. And we've got replication checks. So let's just read this beginning bit here. This chapter is a brief consideration of the problems of fault detection with measurement, control, and data communication systems. For details, the manufacturer's manuals. Okay. So there are a number of techniques that can be used to detect faults. We've got replication checks, expected value checks. That's kind of a brainer. Timing checks. Hey, did the car arrive on time? Did the delivery arrive on time? If it didn't arrive on time, there was probably a fault. Let's check. Reversal checks. Parity and error coding checks. By the way, that might not be true, what I just said about the timing checks. I was just assuming that that's what it is based on the name. I've never actually studied this. I don't actually know, so don't shoot me if I'm wrong. Okay. Watchdog timer. A watchdog timer is basically a timer that the system must reset before it times out. The system must reset before it times out. Why? Okay. If the timer is not reset in time, then an error is assumed to have occurred. The timer is not reset in time, then an error is assumed to have occurred. That doesn't make sense to me. I can't even think how that would make sense. Now I know what you're thinking. You're probably thinking, well, just read the chapter, you dumbo. And exactly, I'm a dumbo. I'm not going to read it. Okay, so parity and error coding checks. In order to try and detect when a data signal has been corrupted and has an error as a result of noise, error detection techniques such as parity checks are used. What? Okay. Okay, that would probably make sense if I read up previously what a parity check was. So I'm going to skip that. Oh, parity has to do with bits and binaries, right? So common hardware faults, sensors, motors, blah, blah, blah. Yep, of course. When you have hardware, things moving, or whatever, then yes, things break. Microprocessor system. Typical faults in microprocessors are chip failure. Okay, so don't ask me why. I'm quite interested in computers and stuff, so not that I would probably ever need it, but feel like this is something that I should just take notes on. So I'm just going to delete all of these. Keep just the overview. So chips. This is the thing. Like if you just if I copy and paste this large chunk of text here, and then do that over and over again, you end up with notes that just look terrible, and you're never ever going to read it. You've got to give yourself a chance. I mean, that's way more digestible than what it was before. Fault finding techniques. So let's go same again. Fault finding techniques that are used with microprocessor-based systems include those listed below. Visual inspection. Just have a look, mate. Have a look. Have a look. See if you can figure it out yourself. Have a look. You're like, boss, I just started today. I don't know. Never done this before. Don't worry. Just go have a look. Look, check the capacitors. Have a look at the capacitors. See if you can see anything. Hate that. Visual inspection. Like it's only useful if you actually have an idea of what corrosion looks like. You've never seen corrosion before, and then someone goes, "You go have a look at that 12-volt battery over there and see if there's any corrosion." And you're like, okay, what's that? Logic pulsar, current tracer. As you can see, I have a lot of copy and pasting issues. Logic, oh dear. Okay. I just want to read over each one of these just to get it into my brain. But there's a lot here, man. What's up with all this? So what is this? This is supposed to be fault finding techniques using microprocessor-based systems, include those listed below. Okay, that's not. There's more, man. Okay, so let's just read this. So we've got typical faults in microprocessor systems are chip failure, passive component failure, open circuits, of course, short circuits, of course, externally introduced interference. Yep, like a rat gets into your microprocessor and decides to chew it. Software faults, fault finding techniques that are used in microprocessor-based systems. Almost fell off my chair there. Include those listed below: visual inspection, multimeter, oscilloscope, logic probe, logic pulsar, current tracer, logic clip, logic comparator, yep, signature analyzer, and logic analyzer. I'm comfortable with all of those. Systematic, I thought I said systemic there. Systematic fault location methods. The following are systematic fault location methods: input to output, output to input, half split. Fault location methods are input to output. A suitable input signal is injected into the first block of the system, then the measurements are made in sequence, starting from the first block and at the output of each block in turn until the faulty block is found. Okay. I think I'm gonna. Well, I started writing about the chapter. Why not finish it, right? Okay. I mean, my brain's kind of checking out now already. So, oops. Input to output, output to input, and half split. I assume is like a combination of the two. Okay, self-testing, emulation, and simulation. Yeah, I've kind of checked out now. So okay, PLC system. This is probably important. PLCs have a high reliability. They are electrically isolated by the opto isolators or relays from potentially damaging voltages and currents at input and output ports. Battery packed RAM protects the application software from power failures or corruption, and the construction is so designed that the PLCs can operate reliably in industrial conditions for long periods of time. PLCs generally have several built-in fault procedures. Critical faults cause the CPU to stop, or other less critical faults cause the CPU to continue running but display a fault code on the display. The PLC manual will indicate the remedial action required when a fault code is displayed. Okay. So we're on PLC systems. So program testing. The software checking program checks through a ladder program for incorrect device addresses and provides a list on the screen, or as a printout or all the input output points used. I'm quite keen to learn about PLCs because I assume if I'm working as a renewable energy engineer or as a power engineer or whatever, I'm going to be using those. That's what I'd assume. So yeah. Okay. Testing inputs and outputs. What's that? PLC has a monitor of systems. PLC can also be used as a monitor of the system being controlled. Okay. Let's skip all of this. Alright, and then that looks like we're done with that chapter. We're on to part 5 now, system models. Alright, so we're going to end this video here, and then hopefully we swing through the remaining 1, 2, 3, 4, 5, 6, 7 chapters, and then 8, the last chapter there in the next video, and then that will be it for this book. So as you can see, I don't know, I think I mentioned it earlier in this video that if I was doing this by myself without recording the video, probably take me an hour and a half, and it honestly is an hour and a half very well spent. I do this with all of my modules, and you might think it's a bit crazy, but you learn loads. You learn absolutely loads. And if you spent 6 hours in one day studying, you could get through 4 books easily. And it's just, yeah, I mean, my brain would kind of be fried after that, but you're able to just learn absolutely loads. Like, this is a hell of a lot of notes here. Like, look at that. And when I go through and I convert all of these notes here into questions and then I test myself on it, it's phenomenal. The results are phenomenal. And sometimes especially last year when I was talking to a lot of my classmates, when I was in the lectures talking to the lecturer, people are like, how do you know that stuff? How do you know this stuff? And you seem like you're a lot smarter than you are. And I think a lot of people, attribute being able to recall, super basic information as being very smart. And you're not really. Like, if I'm able to just say to somebody that, essentially solenoids consist of a coil of electrical wire with an armature, which is attracted to the coil when a current passes through it and produces a magnetic field. I'm just recalling one sentence, right? If I can recall that in class, in a lecture or something, people think this guy's amazing. And it's not amazing. A bit of work. And the fact that you're watching this video and you're listening to this at the end of an hour and a bit video, go you, man. I hope you do very well. Man or woman, of course. So yeah, thanks for watching, and I shall see you in the next video. Peace.